We're going to finish out chapter 2 by talking a lot about carbon and the molecules that it can build when we have many atoms of carbon together. Looking at our periodic table, we see carbon here. And if you remember our trick from previous videos, carbon would have 4 valence electrons. And so that means that typically carbon wants to form 4 bonds. These are often covalent, often non-polar bonds. So if I were to just write carbon symbol, the C, and I'm going to show those bonds sticking out in each cardinal direction here. We'll see in a moment that it's possible for some of these to be double or even triple bonds, but this is what it would look like when everything is a single bond. And I'm going to draw the simplest hydrocarbon. So a lot of what we have are called hydrocarbons because there's a lot of carbons and there's a lot of hydrogens. So this would be a hydrocarbon in like the simplest form. But because of these 4 cardinal directions that carbon's bonds kind of go in, it makes it very, very versatile, and it's actually the building block for most of our most of the molecules in living structures. We'll call these organic molecules. And the organic molecules contain carbon. They're used in life, and they make up living beings no matter what size. So a single cellular organism all the way up to the biggest tree. These are typically made of carbon-containing molecules. We can chain multiple carbons together to build what we'll call macromolecules. Macro meaning large, and then of course a molecule meaning multiple atoms. So a macromolecule can contain hundreds, sometimes thousands of atoms within. So these are typically, like we said, hydrocarbons. If it is a true hydrocarbon, the only atoms present would be from the elements of hydrogen and carbon. These would be very simple. So we'd have propane, methane, butane are examples. Propane, if you have a propane tank to run some of your furnace or heat your home. Methane is often the main component in natural gas. And then butane is actually what we see in like lighters and lighter fluid. And these prop, meth, and bute tell us how many carbons would be in this particular chain of hydrocarbons. And ane, we'll learn in a moment, means that everything is a single bond. So I'm going to go up top of this slide here and draw some of these out. Propane first has 3 carbons. Prop might be new to you. Prop in this case for chemistry means 3. And this is a true hydrocarbon. There are no double bonds. There is only carbons and hydrogens present. And so this would be what the structure of propane looks like. Meth means 1. I drew that out a moment ago, where we've only got 1 carbon. So here's methane again. Bute, it means 4. 1, 2, 3, 4. And so this is what butane would look like. So again, each one of these hash lines represents a single bond where we have electrons being shared. 1 electron from each atom across the bond. In this case, we have all nonpolar covalent bonds. Carbon and hydrogen do not have really much difference in strength for pulling electrons towards it compared to whatever's on the other side of the bond. So this hydrogen and this carbon here, not one is really stronger than the other. And we would look at each of those bonds and see that they're all going to be covalent nonpolar bonds. But what's really cool about these is when we burn them, we release a lot of energy. This item here is ethane. You may have heard of the word ethane. It is an alkane, so everything we've done so far ends in A-N-E, ane, and so those all have single bonds. But it's possible for a carbon atom to form a double bond with a neighboring atom, and so that's what this would look like. So if you look at each of these carbons, they're still each participating in 4 total bonds. 1, 2, 3, 4. And then on the other side, 1, 2, 3, 4. But because we have double bond, we signify that with an ene ending instead of an ane. And it's even possible for these carbons to form triple bonds together, and we would name that ine, an alkyne of some sort. These alks just are placeholders for a prop or a meth or anything else like that. But we're really talking about the ane, the ene, and the ine here. We've drawn all of these out so far in a chain. So like a long chain structure. They can also come in a circular structure, a ring, which we'll also call aromatic. So we're going to talk about these more in depth as we go through the chapter. Okay, so hydrocarbon chains. Hydrocarbon, hydrogens and carbons laid out in a chain form. The fact that it's a chain instead of a ring structure, we'll use the term aliphatic. Aliphatic means a chain structure. So they're going to be laid out in a row, but they could have some branching. So here in this particular image, we're looking at some carbons coming this way. This is what we might call like the main backbone. And then we've got some maybe chains coming off our main backbone. And as you might guess from previous slides, we name those hydrocarbons by counting the number of carbons in the main chain and then seeing if there are single, double, triple bonds present. So again, any single bonds are ane, any double bonds would be ene, and any triple bonds would end in ine. So the example that we had here is propane. That is not this image, just to be clear. But we did draw propane back here in this slide with 3 carbons in the chain. Okay, so aliphatic are chains. Aromatic are rings. And so we name these in much the same way. We count how many carbons are present, and we see if there are double bonds present as well. But we put this cyclo in front of it to show that it's in a circle. So this very first molecule here would be cyclopentane. We've got 1, 2, 3, 4, 5 carbons present in a circle. There are no double bonds. So it would be cyclo for circle, pent for 5, and ane for all single bonds. Here we've got cyclohexane still in a circle. We've got 6. Hex means 6. And they're all single bonds, so ane. This one we'll learn later, or if you take organic chemistry, this one is a little bit special. You see that every other bonding situation, every other bond within the ring is a double bond. This is called benzene, so it's a little bit special. And then here's another one. This is called pyridine. It's also kind of a special case too. It's actually got a nitrogen thrown in there. And we'll learn more about these structures kind of as the chapters go on, the next couple of chapters go on. And we'll also, if you're really interested in this, we cover it a lot in organic chemistry. We're going to talk about something called isomers. Isomers are structures of each other that look really similar. So for example, here is butane. We had this drawn out a few slides ago. But if you look at this thing called isobutane, iso for isomer, it actually has the same number of carbons and the same number of hydrogens, but the chains are laid out differently, right? So the chains are laid out a little bit differently. But it has a lot of the same properties as butane does. So an isomer is something that typically has the same chemical formula. So here our chemical formula, which we haven't really talked about yet. Chemical formula just counts the number of each type of element and lists them out. So butane would be C4H10. And then over here, isobutane is still C4H10. But the placement is a little bit different. So a different type of isomer that we can have is called a geometric isomer. And this is where we have double bonds in place. So these two items here are geometric isomers. And you see they have double bonds in place. But in particular, I want to point out where the rest of this chain lies. So if I wanted to follow through here, I would see something that looks like this. That's kind of like a cup, an upside down cup shape. Whereas this one is more like a zigzag when I'm trying to, go from one carbon to the next in these chains. And so those play implications, actually really big roles in things like butter versus oil. Why butter is often, solid at room temperature and oil is not, even though they're much the same chemical, which we'll learn about in the next chapter. We'll see, I'll come back in a moment, we'll see that this structure in lactic acid has a structure that looks more like this. But here we have that kink, that cup shape. And so one of these will actually be able to line up nicely with others of the same molecule, and then some will not. Okay, so just a really quick kind of mini recap on what we've done on structures of some types of carbon compounds. We've got methane, all single bonds. That's this structure here. Ethane, 2, that's this structure here, all single bonds. Propane we worked a lot with. We've got some isomers. So we saw butane with 4 carbons, and isobutane also has 4 carbons. Here's an example of isomers of pentane with 5 carbons. And this one also has 5 carbons laid out in different structures. We're not going to get too deep into this for our course, but I do want to point out that it is possible for other atom types of other elements to come into play here. So for example, it's possible for us to start with this kind of methane structure and add something like a chlorine in or iodine in. And now we're no longer talking about true hydrocarbons. This originally had a hydrocarbon base. Or a hydrocarbon basic structure, but now we're replacing it with other molecules or other atoms. So an example of that here is chloroform, which you might have heard of, where we take that single carbon center and we replace 3 of the hydrogens from methane with chlorine. We also have what's an alcohol here. OH, we'll see in a moment, is an alcohol group. And then again, we're not going to talk too much about benzenes here, but these are some just examples. We'll see a lot of salicylic acid. We have some implications of aspirin and wintergreen oil. For the most part, though, what we'll see is we'll have a long chain of carbons. So far, we've only talked about chains of carbons that had maybe even 4, maybe 6 carbons in them. But we can have a dozen. We could have 18, 20. So some of these carbon chains could be quite long. Ring structures, not so much. Ring structures, we have usually typically maybe 8 in a ring, carbons in a ring. But the chain structures can get quite long. And so what we would have then is this hydrocarbon backbone. And we would then have potential for a functional group that could be somewhere within it. And so those functional groups include those other atoms. So if we had a chlorine, that would be something functional. And the reason we call them functional groups is because our carbon-hydrogen bonds, those backbone, the main structure of hydrocarbons, are pretty inert. They don't do much. They're really quite stable. So the carbon-carbon bonds, the carbon-hydrogen bonds are really quite stable. It's when we start introducing different elements that we have a point of action for our molecule. So if I have a molecule containing all carbons and hydrogens and a chlorine, and something's going to happen, some chemical reaction is going to happen, most likely it's going to happen at the chlorine site. We have many of these functional groups, the ones that would have chemical function, and we're going to have an assignment to go along with this so you can understand the functional groups better. But we have what's called, I'll just go over kind of some of the most common ones. Hydroxyl, also known as alcohol here. And this R represents just a random, R for random, number of carbons in the chain. And so every point here that I draw represents a carbon atom. So in this example, I'd have 1, 2, 3, 4, 5, 6, 7 carbons in this chain, and hydrogens would be attached. And we're lazy. We don't draw hydrogens in unless we have to. And so this functional group, somewhere in OH, would be an alcohol, or hydroxyl is another name for it. A hydrogen-oxygen bond is polar, so this could be a place for something to come on. A methyl group we're not going to talk too much about. That's just another carbon sticking onto our chain somewhere. A carbonyl, though, is something that we've got sometimes in the middle. It could possibly be the end. Somewhere in our chain of carbons, I'm going to draw, in this case, the chain of carbons going off in either direction here. Again, every point, every peak represents a carbon atom, and its 4 bonds, even though they're not drawn, would be filled in with hydrogens. But here, this carbonyl is a carbon double bond oxygen somewhere in the molecule, and so this is a point of contention as well. It is polar, so it has polar properties. A carboxyl group, or sometimes called carboxylic acid, is always going to be at the end of the chain because our central carbon will be connected to the chain itself, of course. It'll be connected to an alcohol group and have a double bond going to an oxygen. So that takes up all 4 of its bonding capacities. So this whole unit here is called the carboxyl or carboxylic acid. And amino, can be somewhere in our chain as well. And in fact, this is showing that it's got a nitrogen with 2 hydrogens. It's always going to have a nitrogen, but it might even be in kind of the center point of a molecule. But just the amine, I always think of amine as kind of ammonia or ammonium, which we'll learn is very nitrogen centered. We can also have what's called a phosphate group. And so this comes typically at the end of a chain of carbons. And so we've got a really large structure here where we've got a lot of oxygens, a couple of alcohols, and a phosphorus in the center. And so this is quite active, and this is really important for our cells to regulate energy. We can also introduce a sulfur group, and can't see this very well because something's in the way, but there's a hydrogen down here. I'll write it in red. Hydrogen right there. And so it looks actually and behaves a lot like an alcohol up top. And it would be on a chain of carbons, of course. So the R stands for. And we just have a sulfur with a hydrogen attached to it. And so we can have some of our molecules use this for some pretty important roles. Okay, we're going to use our functional groups and talk about them quite a bit in chapter 3. And they play a really big role in understanding how proteins are created and understanding how DNA is created and how those protein and DNA can function. But even with that said, this chemical structure isn't necessarily our main focus of the course. So I do encourage you to get familiar with these functional groups, but not to be terribly bogged down and overwhelmed with them. They are important because their presence kind of dictates how our biology and our physiology can act. But this is not a chemistry course, so please keep that under consideration. And just to kind of recap a little bit, the carbon and the hydrogen atoms, they bound together through nonpolar covalent bonds, and those typically form what we call the backbone. Sometimes that backbone looks like a chain with even branches. Sometimes that backbone is more of a ring structure. But these functional groups can be introduced at different areas of this chain or ring structure and can have their own properties. So oftentimes these would not be polar covalent. These are oftentimes polar covalent. So let me rephrase that. A lot of times functional groups have polarity and so can interact with molecules nearby in a way that the rest of this carbon-hydrogen chain would not. And so just to kind of bring this into perspective, we've got what's called an alpha helix here. We'll learn a lot about this when we talk about DNA. And so we're actually bringing down some of these structures from our DNA, and we're looking at like hydrogen bonding between functional groups here. So here's an alcohol functional group, and here is kind of like an amine functional group, and here's another amine, and we actually see hydrogen bonding occurring between them that's represented here by these dotted lines. And so we've got another kind of amine and an amine from two neighboring parts of a DNA molecule, and they're hydrogen bonding. And so that's actually, if you've heard that DNA has a helix structure, that's actually how it keeps that structure. So we'll look at that more in depth when we get to DNA.